Hello everyone and welcome to the OAI SAE Aircraft Electrification and Alternative Fuels webinar. I'd like to invite Kim Halizna from the Ohio Aerospace Institute to welcome everyone. Kim.
Good morning. Thank you, Becky. Welcome everybody. And yes, my name is Kim Halizna. I'm the Director of Global Development and Programs with the Ohio Aerospace Institute. And I think it's been a couple of years now that we've put this MOU together with SAE. And the thought was, we wanted to work together and collaborate on things like webinars and really putting programs together for industry and for getting the word out to companies and educating them on what SAE has to offer and encouraging them to become involved in committees and communicating, what OAI has to offer to SAE members, doing joint programs, encouraging SAE to participate in our events, giving discounts on professional development, and really putting together events and educational programs and things like this that are of interest and useful to organizations and industry. So we will be sending out a survey after to determine if, what other kind of training would be of interest to companies. So please do let us know. We will be doing more training like this. We would like to start doing, if there's interest for companies to have in-person trainings, SAE certainly can do that. They even come to companies and do courses. So, please do let us know. And so with that, I'll turn it back over to Becky and enjoy the program.
Thanks, Kim. So my name is Becky Lemon. I'm the Industry Program Manager in Aerospace Standards at SAE International, and we're bringing this webinar to you today. So we will be recording today's webinar. If you have questions, we ask that you enter those into the chat feature, and we'll manage those towards the end of the webinar. We also ask that everyone remain on mute unless you're speaking. And today's agenda is a packed agenda. We did our welcome and introduction, but we have an overview of SAE International's Aerospace Standards Program from Jonathan Archer, the Director of Aerospace Standards Strategy and Innovation at SAE. We have an overview of SAE's standardization activities on aircraft electrification and alternative fuels from Pascal Talon, Director of Aerospace Standards Technology and Innovation. We have Ed Lovelace, the CTO of Ampaire and Vice Chair of E40, presenting the E40 Electrified Propulsion Committee activities. We have Olivier Savin, CEO, Blue Spirit Aerospace and Chair of the AE7F Hydrogen and Fuel Cells Committee. He'll provide an overview of those activities. Then Thomas Taylor, Technical Fellow at Boeing and Chair of the AE10 High Voltage Committee, will provide an overview of what's going on with the AE10 committee. We'll take a short 10-minute break, and then we'll move on to the AE11 Aging Models for Electrical Insulation in High Energy Systems Committee. Wei-Jin Yun, Senior Principal Engineer, GE Research, and Chair of the AE11 Committee will provide those details. Then we have the SAE A6B3 Electromechanical Actuation Committee. So James Babinski, Vice President of Engineering from UmbraGroup and the Chair of the Electromechanical Actuation Committee, will present. We have a presentation from Tim Davidson, Corporate Sales at SAE, who will speak to us about the SAE Mobilis and OnQ digital standard systems. Then I will present on how to get involved in SAE's Aerospace Standards Committees. We'll do some Q&A at the end, and then we'll do a wrap-up. So let's move on with today's presentation. I invite Jonathan Archer, the Director of Aerospace Standards Strategy and Innovation, to present the SAE Aerospace Standards Program overview. So Jonathan, welcome.
Good morning, Becky. Good morning to you all. Thank you. As the title says, I will give you a brief overview, background to who SAE is, the aerospace program, and provide Pascal with a lead-in and a short overview of some of the programs that form part of the sustainability and electrification program. Next slide, please. So in broad terms, SAE provides a neutral forum to enable industry, government, any stakeholder that has an interest in aerospace standards, in problem solving industry issues with an outcome that is invariably a consensus-based standard. They can take a couple of different forms, but the idea being is we provide solutions to industry and the broader community through leadership, through education, through providing, as I say, a neutral forum where people can come together and discuss their issues and move technology, particularly mobility, forward. We've collected and coalesced a number of themes from a technology perspective that help bring those people together. Although they're shown as 10 individual items, as you'll see today, they're actually all very connected. Advanced manufacturing obviously involves advanced materials. Advanced propulsion involves both of those, but also cybersecurity, the connectedness, providing data, and increasing levels of automation. Same with electrification, that increasingly includes the connectivity, the use of blockchain, the need for cybersecurity and advanced computing. So there's no one thing that stands alone. They're very much connected. Next slide, please. So who are we? Here's a quick overview of where we started in 1905 as the Society of Automobile Engineers. But by 1917, it became very apparent because of the work that Orville and Wilbur Wright did from their roots as bicycle mechanics through to aerospace engineers, that this was a perfect forum to develop and coalesce the conversation, not just about cars, but the broader translation into moving people. So today, both the automotive and aerospace standards groups have over 10,000 active standards, covering everything from simple cars and micro mobility all the way through buses, trucks, and the panoply of the aerospace program, which we'll go through in a moment. They both work by a set of common standards and have common goals, the industry and for the technology. Next slide, please. So the beginnings from 1905 with cars and being the Society of Automotive Engineers. Next slide, please. Next. Through to 1916, Elmer Sperry was a very prominent member, and he looked at what SAE was doing at the time and came up with effectively a new phrase that he coined: autus, Greek for self. Next. Motivus, which is obviously Latin for motion. When you bring those two together, you get automotive, which means self-propelled. So next. So really is bringing those things together. Although it's very synonymous with the automobile industry, automotive is coined to represent any self-propelled vehicle, which really coins and summarizes very succinctly who SAE is today. Next slide, please. So although we've been together for over 105 years, from an aerospace perspective, our first standard first international standard was the humble spark plug. This brought together the industry from the USA, Great Britain, and France to bring together the fundamentals of who we are. It really is in SAE's DNA to be international. We may be headquartered in Warrendale, Pennsylvania, but we have members from all over the world. Next slide, please. And this is part of the broader program that we represent. There's over 180 technical committees under the Aerospace Council, broadly into 10 groups, 5 steering groups that provide perspectives for roadmaps, gap analysis, and help direct some of the committees with new tasking. So as you can see, it's a significant undertaking covering everything from raw materials through to operations and maintenance. Next. So by the numbers, as you can see, we've been around for at least 105 years. Within our community, there are over 7,800 active documents produced by 180 technical committees and over 11,000 participants. Since 2017, we've created 25 new committees and steering groups to basically embrace the newer technologies of which we're going to be looking at today, with over 1,300 standards in progress. Next slide, please. So what do we do? As I said in my introduction, we bring people together. Obviously, there has to be a need, and we have to have sufficient people with sufficient experience and expertise to provide the necessary information to form or develop a standard, which is provided by the committee structure. The Aerospace Council provides governance and oversight and makes sure that the rules and regulations that govern the association are adhered to and enable the publication of our standards within our marketplace, online marketplace, which is Mobilus. The next slide. So whereabouts do standards fit in the broader ecosystem? Although we appear at the bottom as part of industry standards, and there are other associations that support that body of work too, they apply both from a government perspective, but also from an ICAO perspective too. We have a couple of taskings that were given by ICAO to do with the carriage of dangerous goods, in this instance lithium batteries, that will form part of ICAO's SARPS manuals, which apply to or for the regulation of international travel. For those of you who don't know, ICAO is actually part of the United Nations and enables world travel. So when you land at an airport in France and you take off from somewhere else, that everything is the same way, the signage, all the information is the same. To coordinate the design, manufacture, and certification of products, we have FAA, EASA, Transport Canada, and ANAC of Brazil, who we interface with to provide means of compliance, additional information to support the regulation and certification of products. As you can see, it's quite a dynamic process. Next slide, please. Talked about the Aerospace Council. Who are they? At the moment, there are, I think, 33 companies, government organizations, operators, researchers, universities, a broad panoply of people interested in ensuring that the standardization process is open, engaged, and addresses industry and governmental needs. Next slide. So, as I said, there's about 25 new committees that have been created over the last 5 years or so. Here's a selection of those things. As you can see, those starred have been requests outside of SAE to form committees, and the last four in red are those that we've done over the last 12 months or so. Formation of two steering groups, one for supersonic aircraft and the other for sustainable alternate fuels. An important committee, S18H, looking at the human factors considerations of the safety assessment process. That's ARP 4754 and 4761. And then finally, the G36 is a Sustainable Waste Management Committee, which will formally kick off on the 14th of this month. A look at initially international waste, or waste generated by international flights. It's going to be an interesting committee, and I think going to be very wide-ranging once it gets itself started. Next slide, please. And we're talking about Ohio and the aerospace community in this state. Your state is very rich and very diverse. There's over 1,300 total participants in our program, with over 289 voting members. You provide us with 12 committee chairs, 5 vice chairs, and importantly, four secretaries. As I say, those numbers are dynamic as the committees go through, evolve, but very key contribution to our overall program. And importantly, GE Aviation is a council member and provides a great resource and feedback on how the program is moving. Next slide, please. And from a leadership perspective, as I say, it's a very diverse, very technology leading group, from additive manufacturing, de-icing and aerodynamics, polymeric materials, wheels, tires, and brakes. That's a very important area, certainly from aviation perspective. In-flight propulsion management for engines. Yeah, and right down to aerospace engine supplier quality. That's another key topic area that provides a strong underpinning for the broader aerospace community. Next slide, please. And also, it provides a very rich group of organizations that support our committee process. Again, these are the key ones. There are some smaller organizations, but fundamentally, AFRL, Raytheon Technologies, as I say, GE, Honeywell, L3, Parker Hannifin, which most people know as Meggitt, NASA, obviously Ohio State University, and the University of Cincinnati. Again, without you, our programs don't exist and standards don't get developed. So thank you. Next slide, please. So we're here today to look at alternate fuels and electrification. Looking at things from an environmental perspective, because that's a very strong driving force in shaping our agenda. I've broken out some of the committees just slightly differently than you perhaps normally would. So from a hybrid and electric propulsion system, you can see, as Becky introduced, E40, AE7 for alternate fuels, AE10 and 11. From more of an electric aircraft and fuel cells considering hydrogen, you gain AE7, A7F. The AE5 provides us a strong lead on the alternate fuel SAF and fuel systems. With the introduction of lighter aircraft, wanted to go faster on smaller propulsion systems, particularly batteries, you've got to find something that lightweight materials, composites, parts that are additively manufactured. And the AMS group provides 3 committees, AM, P17, and CACRC, with that expertise. But further, as we look at the environmental issues, you've got to be able to measure the emissions that are coming from those aircraft. That includes noise and engine particulates. And AE20 and E31 provide that detail. But we're also looking at how we replace some of the hazardous chemicals that are used within aerospace with more friendly, REACH compliant products. And the AMS metals and non-metals, the composites and plastics groups, are helping with those activities. Next slide. So a completely different perspective from an electric aircraft perspective, and many of these aspects we're going to get covered today. But you can see just from an electric aircraft perspective, how many committees provide inputs from charging, from batteries to improved lighting to EMC and lightning effects, the need for standards and specifications to deal with new high voltages, cybersecurity, alternate approaches to safety assessments because of these new technologies. So as I say, just looking at it from a very, very different perspective. PNT, position, navigation, and telemetry or timing is fundamentally GPS, is how that interacts with not just the aircraft system, but the community in general. So next slide. And finally, how do we bring all this together? You know, I talk about the piece parts, but part of what one of the strengths of SAE is to bring these communities together. Part of that is through cross-sector synergies, because the mobility is changing. The transition between mobility sectors is changing. There is more data. There's greater need for cybersecurity. So autonomy. Things are reducing pilot workloads, automated driving systems. All of those things play into how we've been introducing, electrified vehicles or vehicles that use alternate fuel sources, whether that's a biosaf, whether that's hydrogen. They're all becoming more and more interconnected. And fundamentally, it's to keep people safe. So you need standards and specifications looking at crashworthiness, both from a ground vehicle and from an aerospace vehicle, and also the crossover of those vehicles that now transition from being a car to a fixed wing aircraft. So it's a, as I say, a very dynamic and changing picture that is now reflecting the way people want to live and travel. Next slide, please. As I said earlier, with regards the availability of our standards in a digital marketplace, we use Mobilus. SAE isn't just standards. We publish magazines, books, technical journals, edge reports, which are basically unsettled technology, things that are still maturing, are still need to be shared and discussed before we can even think about developing a standard. So interested, Mobilus is the place to go and find all of these materials, including standards. So next slide, please. Finally, we do a series of events each year. Aerotech will be held in Fort Worth, Texas, next March 14th through 16th. But we also have Convec and WCX from a ground vehicle side. All of those conferences provide high-level perspectives on new technologies, our current programs, great networking and learning opportunities from a very diverse group of people and technologies, predominantly from an aerospace standard, but as I say, WCX and Convec provide the same opportunities from a ground and commercial vehicle perspective. And finally, next slide. Without you, our programs don't exist. So if there's anything of interest that I've covered that the following speakers don't provide coverage of, or how to get engaged, or how to work with SAE in very different ways. As I say, we offer all sorts of training, educational programs, K through college, but also post-professional development too. So please reach out to any of the SAE staff and we'd love to connect. Thank you. Thanks, Becky.
Thank you, Jonathan. And we have Jonathan's contact details here. If you have any questions for Jonathan, feel free to reach out to him. Or if you have questions you would like answered during this webinar, pop those into the chat feature and we will address those later. So our next speaker is Pascal Tallon. He's the Director of Aerospace Standards, Technology, and Innovation at SAE International. And Pascal is going to present an overview of SAE's standardization activities on aircraft electrification and alternative fuels. So welcome, Pascal.
Thank you, Becky. Good morning, good afternoon, everybody. This is a great opportunity for me to share information on what SAE is doing with respect to electrification and work on alternative fuels. So I'm Pascal Tallon, so Director of Aerospace Standards, Technology and Innovation. So let's move on to the next slide, please, Becky. So here we have 4 clicks, so we need to go through this. Yeah, this is the first click. So this slide actually is showing different boxes. So this is a bird's eye view. What these boxes actually are outlined in blue color, meaning that you can see that the top of the slide on the right hand side, there is coordination and guidance trickling down from what we call the Electric Aircraft Steering Group, which is composed of the industry. Of course, the work there is really to identify the needs in terms of standards, any gaps that may exist to develop and certify products, and also build roadmaps. So in these boxes, actually, we can see that typically in terms of electrification, we find E40, and that is the electrified propulsion. We call it electrified because we have full electric versions, but also commonly called hybrid electric versions, meaning that we have a proportion of electrical energy being used, but also a proportion of conventional fuels. But these conventional fuels are slowly changing to sustainable alternative fuels as well. So that is the first box called electrified propulsion. So you will get information from Ed Lovelace, who is the vice chair of that committee, just after my speech. So next to that box, you can see that we have what we call high voltage and high energy. There are 2 committees there, AE10 and AE11. So once we start dealing with electrification, whether it's for automotive or in this case for aerospace, you would end up ultimately with high voltage powertrains because of the fact that you need to go up in voltage in order to achieve power dense solutions. So minimize the size and volume of equipment, but also wiring. So, but that is bringing other challenges. So that's something that we will be sharing today during this webinar. So then in terms of within the high voltage powertrain, you can see that I mentioned the wiring side of things, but also we have power and equipment, and we have a couple of committees there. So A7X, A8X, we put in an X because there are a few committees, so dealing with many aspects of power and equipment. So AE7 is power and equipment, and within AE7 we have also fuel cells as an equipment, so I'll come back on that. AE8 is to do with wiring and any interconnect device used for wiring, and AE9 is for materials dedicated to electric systems. And then for an electric aircraft, we do need to charge on board batteries. So with respect to how we manage that charging and how it is done, depending on the size of the aircraft and the needs of the aircraft, we do have different workflows for different aircraft segments. For VTOL, which don't have the same needs as regional aircraft and large transport category aircraft. So that's AE7D, energy storage and charging. And The last box there showing actuation. This is really the end user, the systems which are going to make use of any electrical power which can be used on board. So typically today the discussion will be on totally electric actuation, commonly called electromechanical actuation. The small box which you see on the bottom of the slide is really the committee which is called H3, which is there to support the aircraft operations on ground. So all that is needed to, for instance, service and support the aircraft on ground. Next click, please. So as I mentioned, this will be discussed later, so we can carry on. Next click. Yeah, this will be discussed today. So now coming to the alternative fuel steering group. This group was created this year, so very recent. So I'll be expanding a little bit more later during my presentation on this one. Whereas the EASG, the Electric Aircraft Steering Group, has been operating since of many years. So this alternative fuel steering group typically is going to look at two types of fuels: sustainable aviation fuels, which is the current replacement in a blended manner with kerosene, but also hydrogen. So so coming to hydrogen, so AE7F is the committee dealing with both hydrogen and fuel cells. So Olivier Savin is with us today, who is the CEO of Blue Spirit Aero, will deliver a comprehensive overview of what this committee dealing with hydrogen and fuel cells is doing right now within SAE. Just next to this box, you can see that we have AE5X committees. So these committees are really working on how any type of fuel, when it goes on board, would have to have fuel systems, monitoring, metering, distribution, lubrication, and also inerting. So today I'll just explain a little bit on what we're doing here with respect to the new types of fuels coming up, and namely sustainable aviation fuel. And once again, we need ground support equipment for any type of new type of fuel, and this is a challenge as well. So next slide, please. Yeah, this is something I just also previously mentioned. So E40, just really a bird's eye view of what E40 is. So I have put in a complex diagram just on the right hand side just to show the intricacies that we end up having when we deal with hybrid electric solutions versus electric solutions, because of the fact that we still will be dealing with different types of energy sources. So we mentioned batteries, we also mentioned fuel cells. So all this will somewhat be has to be optimized. So this work is undertaken by the Electrified Propulsion Committee. So this committee addresses the considerations for performance of the electrified propulsion within the safety, integration components, as well as any type of interface that you may find within the system, but also as an interface with other systems. Next slide, please. AE10, this is really a very high-level overview. So electrified propulsion cannot be, I would say, implemented without dealing with the high voltage powertrains, which typically are going to bring the energy source in whatever form it may come, electrical energy or from any other source like hydrogen. So you need to go up in voltage. That's what we mentioned previously. So there's a need for standards, and this is the industry is getting together. So this committee was created last year, and since last year we have more than 200 participants. So it just shows really the interest of what's being done within this committee. So the overarching, I would say, committee driving the coordination of the work done by E10 is called the High Voltage Coordinating Committee. And then within the committee, and Tom Taylor, who's technical fellow at Boeing, will really expand what's happening right now within these task groups that you can see just underneath the high voltage AE10 box. So in terms of task groups, we have systems, energy storage, source. Here we will be looking at how the integration, the way different types of sources will work together. EWIS is the electric wiring and interconnect system. Equipment device, that's how are we going to switch power and distribute power. So that's one part of it, and power electronics will be part of it. So user safety, when we say user safety, we are talking about actually the safety from a maintenance personnel perspective, but also from a passenger perspective seated in an aircraft, but also, of course, the crew's safety as well when they operate an aircraft. Last but not least is the infrastructure, and that's also linked to what I just mentioned previously, all that is needed to support and service the aircraft on ground and its operations. Next slide, please. So AE11, sorry, is the aging models for electrical insulation high energy systems. So why this specific committee? The reason being, when we go up in voltage level, the insulation which is used in the wiring is going to experience, when you go up in altitude, some physical phenomenon called partial discharge, which has the effect of actually kind of somewhat, if care is not taken, once again, degrading the insulation, so reduce the lifetime of the wiring, which actually would compromise the lifetime of operation of any system on board. Reason why, so this committee was created to identify the failure mechanisms of the insulation, especially with respect to higher altitude. So when I say insulation, it's not just the wiring, but it also ends up in all the electrical machines, and this is to do with the insulation of the windings in the machines. So the idea here is really to analyze the impacts on the physical properties of these. Like I explained, the partial discharge phenomenon, and the ultimate goal here is to define a multi-physics, so it's electrical and both thermal as well, model for the aging phenomenon. So Voyaginian, formerly with GE's research, will be providing a comprehensive explanation of where we are today with respect to A11. Next slide, please. So, so when we discuss electrification, we talk a lot about batteries, fuel cells, of course, and we know that fuel cells use hydrogen. But what about sustainable aviation fuels, which is the current trend to achieve sustainability goals for operations? Like, I mean, when you start mixing kerosene with SAF, but when you think about it, actually SAF could also be used to generate electricity on board using gas turbines as well, which is one third option to generate electrical power and energy on board. So I mentioned batteries, I mentioned fuel cells. Now we could also produce electricity on board with gas turbines, but operating not from kerosene, but from sustainable aviation fuel. So two fuels we'll be addressing will be SAF and hydrogen. Next slide, please. So this is just to give a flavor of what is going on within one of our fuels committees, which is the AE5A. So there's a work in progress on jet fuels from alternative feedstocks. So this is to provide information on the introduction of jet fuel produced from feedstock other than the traditional petroleum crude oil. So the rationale behind is to kind of define and introduce these fuels to supplement petroleum-based fuels. And the idea here is really to address the general aspects with respect to any specification that the industry and military is using to implement and expand utilization of this fuel. Next slide, please. So one single slide on hydrogen fuel cell, and this is a huge story because of the fact that this is a committee which is running and operating since many years, and this is a teamwork between SAE and EuroK. So it is showing once again that SAE is international and knows how to seize opportunities to collaborate with other standards development organizations. So I won't get into the details here. So Olivier Savin will be providing a detailed overview later today. Next slide, please. I wanted to share some information on this new steering group called Sustainable Alternative Fuels, created this year, and having a very broad, I would say, ambition because of the challenges behind the implementation and utilization of these fuels. So once again, this is a repeat, but when we say sustainable alternative fuels at SAE, it's both sustainable aviation fuel, SAF, and hydrogen. So this group is not writing any standards, but the idea is to really have an overarching holistic approach and strategically identify the needs for standardization and the roadmaps, associated roadmap. So to do that, we go from the fuel producers right down to the end users. And you can see that the membership here involves the full value chain from fuel producers down to airport planners and authorities. And on the right-hand side, you can see that we have all the various topics that we are addressing. And once again, storage, how to store fuel on board is one of the key challenges there. And safety is also a paramount aspect that we would have to discuss here and identify all the workflow that the committees then will take over in order to build and develop standards. So in a nutshell, the steering group typically is going to identify the standards requirements. So we have we kicked off this group in May, and we have more than 50 visionaries and experts building the roadmap and devising and analyzing the needs per se. So when time is ripe, we can delegate work to any committee which has the expertise to build standards. And there is a case in point right now, and this will be news in the very near future. We are building work within AE5 committees to tackle the hydrogen refueling standards need, which is trying to establish commonality between commercial vehicles and aeronautics, aerospace. So typically liquid hydrogen and gaseous hydrogen. So next slide, please. So I'm not going to go into the detail. This is really to give a handle to the audience on the spectrum of what we are trying to achieve with this SAFSG. And you can see that there are many task groups which deal with specific portions of the value chain. The first one is on the fuel production, how it gets into the airport, because today hydrogen is existing, SAF is existing, and once again, when you get all this into an airport, you need to figure out ways and solutions and harmonization and standardization routes so that this can be implemented seamlessly and without hassle. Next box, second box is showing really the infrastructure side of things. And you can see that, I mean, once again, any type of fuel getting into an airport could have the need to get processed on site, like, I mean, bringing gaseous hydrogen, then changing it to liquid, and SAF is also part of it as well. Third is to do with the systems. So for new fuels, anything that you will have to deal with, you know, at the systems level in the aircraft. Propulsion systems, these are the key components, large components, let me say, on how to deal with these new fuels. So we have a task group on that. Emissions, of course, I mean, even though we say that with these new types of fuels, you're going to reduce emissions, we still need to characterize and define the tools and methods to measure the emissions. Like they could be noise, but could also be particulates, could also be gaseous emissions. So this is something that we deal with. And SAE committees provide a reference to any type of emissions related standards with respect to what is expected by ICAO. Testing is the last, I mean, the other one. Safety, reliability, once again, as I mentioned previously, I mean, due to the nature of these fuels, extra care and extra attention has to be taken into how everything is monitored and safely implemented. Of course, and in the group, we do have airlines working with us to identify the challenges that they see from their end as well. So yeah, this is what I have for today. So Becky, we could probably move to the next slide. Yeah, thank you for your attention. I mean, and over to Becky for the remaining portion of the webinar. Thanks, Becky.
Thank you very much, Pascal. Great presentation.
Welcome. Thanks.
So our next speaker is Ed Lovelace, a vice chair of the E40 Electrified Propulsion Committee. So welcome, Ed.
Yeah, thank you very much. Happy to be here. Yeah, so as you just heard from Pascal, he gave a good overview of how E40 fits into the rest of the sort of SAE organization of committees. As was already introduced, we are specifically focused on electrified propulsion aircraft applications. And the point was very made clearly that this is meant to encompass both fully electric and hybrid electric and be relatively agnostic to energy sources that might be used in those applications. Next slide. So this is some of the key information for the committee. If you want to get involved, you can find the committee page. We have a committee manager if you want to become a member or have a different participation level. You can reach out to Lisa Brown. I'm going to talk a little bit about the current works in progress. We've got 5 that have been officially kicked off and some documents that have been published already. Next slide. So this gives you just an overview of what our scope is. And the kind of the key point that I'll make here is it's not solely just at the propulsion system level, but how that propulsion system integrates at the aircraft level. And this is important for serving the industry in order to aid them in going through the development and certification process of these projects. There's a definition activity, so of course people can have a common understanding and language used in terms of communicating about these subsystems. And then some of the key attributes that the standards will cover over time are performance, airworthiness, safety, aircraft integration, and then, of course, interfaces between different components and subsystems. I'll talk on a later slide a little bit more about how we use the ambassador role. Next slide. So in terms of formation, but I can't believe it now, we're actually at just having our 4th anniversary on this committee. We, of course, got together in the industry across really a wide range of skills and experience, including aircraft OEMs, Tier 1 propulsion companies, regulators and authorities representation, as well as a number of the subsystem and component manufacturers. We had infrastructure expertise and even aircraft operators involved in establishing that there was a need, that there were gaps that needed to be filled, that would aid in developing some of these projects, and then set about developing the scope. Of course, SAE, which was involved through the EASG group, had helped galvanize starting these meetings, but that was all approved in November of 2018. Next slide. So we use surveys in the committee quite often because there's such a wide range of new activities associated with the electrified aircraft, and tried to develop a roadmap through a number of surveys in what was important, what was not covered by existing standards. And I'll maybe just make a few high-level comments here on this. One, again, trying to keep focused on the North Star of serving the industry. But one of the other guidance items that we really drove towards was focusing, since we can't do everything all at once, focusing on supporting what we perceived as an industry as the nearer term projects and needs, and that really falls into needs for both the industry for ways to analyze their subsystems from a safety perspective, provide means of compliance, and that gives them two purposes again. Helping them with their certification applications, but also in the development of their supply chain and appropriate ways to specify and organize that. For the authority side, this helps with filling in some of the gaps in existing regulations that don't specifically address electrified propulsion. The other sort of guiding principle for us was really based on the fact that this market is relatively new. I mean, we're near a market penetration of 0 today, but there's quite a bit of activities in a number of companies across a wide range of applications. So we want to make sure that we do a balance between over specifying and under specifying standards in order not to presuppose that we know every kind of configuration that's going to be commercialized for electrified propulsion, and also to recognize the relatively short history in some of the supply chain elements. So conventional combustion engines for aviation have decades and decades of experience, but some of the new power electronic systems that are being applied now to aviation have relatively shorter histories. So we're trying to develop standards for how to go through the safety analysis for some of these new technologies that are being developed for electrified aviation. Next slide. So at the very beginning, we identified a number of potential new publications from the membership, again, falling into a few buckets: safety and certification, design and operations of systems and aircraft level, and some more specific technical standards. Next. We then used this to develop a prioritized roadmap with, as you can see in the top right corner, would be the most urgent and important certification activities. And again, this naturally is trying to serve the portions of the industry that are trying to develop applications towards commercial aircraft today, how to address that from a safety continuum standpoint. And then moving down from that top right corner, some of the key subsystems that maybe have the largest gaps in terms of regulatory means and methods of compliance. Next. So we use an ambassador function. We have a number of our members that are members on other SAE committees or committees outside of SAE. And because there's such a huge number of committees, everybody's busy, we want to make sure we're not duplicating work that is being handled by other committees, and coordinate how to interface and make sure that the standards we're developing are consistent. And Pascal talked about a few of these committees as well. Oftentimes we're either having a member of E40 that is also a member of one of these committees, or in cases where we don't have that actively, we're interfacing with either the chair or vice chair of those other committees. Next. We have plenary meetings twice a year, typically in September and then in March. We just finished our 7th plenary meeting in San Diego earlier this fall. And this gives you a good overview of the way we operate the plenary meetings. In between the plenary meetings is where a lot of the real work is done. Each of those work groups that I'm going to run through sequentially holds virtual meetings some typically every 2 weeks. For some of the more urgent ones, we have some sprints where the teams might be meeting once per week. But then we get together as a full committee twice a year. Typically, we will have some presentations from industry. And this is important for sort of reaffirming whether we're focusing on the highest priority activities for the committee. This is an opportunity to identify some new gaps that are emerging that we might turn into work groups. Then, as you can see in the later half of the day, we typically break out into the different document preparation subgroups, so that we can have some dedicated face time to make some diligent progress and review what's been handled virtually over the previous 6 months. Next slide. Meetings are typically 3 days. Again, we'll have the breakout sessions for the first few days. The other key aspect of E40 is extremely active participation from the authorities. And again, as has been pointed out by Jonathan Archer, this is very much an international effort. So we have authority representation from FAA, from EASA, from Transport Canada, and often from some of the other regulatory bodies in other parts of the world. The Japanese authorities are very active in the E40 activities as well. Next slide. And the other key feature of the regular meetings, of course, is reviewing the publication and other activity roadmap for the committee to make sure that any adjustments that need to be made based on priorities occurs. We also, as we enter into these sub-work groups that are created, we need to make sure we have enough membership and skill representation across the group in order to make diligent progress on developing a standards. So usually the last day is when we propose and finalize scope and rationale for any new work groups that we're considering. Next. Okay, so I'm going to go through quickly some of the active document standards work groups that we have. The first one is the nomenclature and definitions. Next. So as is pretty obvious, this is helping to have a common understanding of terminology across the industry and with the authorities. It's very much linked to the next work group you'll see, which is the architecture work group. And so they have worked hand in hand, both in terms of making sure that terminology is used consistently in the architectures and defined well in this document, and also to make sure that they're on the same kind of publication timeline. Next. So the first release of this happened in August of this year. There's already a pipeline of additional terms that were deferred for review and potential inclusion for a second release. So there's already a need of work to be continued on this activity. Next. The second document work group is, again, the architecture group. Next. And, you know, as you can see here in the diagram on the right, and Pascal also showed a good overview of the breakdown structure that we created in order to sort of consistently describe the potential interconnected systems. A number of these subsystems don't, of course, have to be required in every architecture. You know, an obvious example is gearboxes won't exist in every implementation of this system. One of the key items I'll notate is that in a lot of these subsystems, we have sort of separately pulled out and defined the controller. So the brains that is conditioning the power flow and operation of some of these subsystems and separated that out from the actual power processing that might be part of the subsystem in an electrified propulsion architecture. But this helps with establishing how these different subsystems interface. What are the key attributes that should be considered in safety analyses and in terms of communicating with the authorities. Next. This one also has gone through a first release in August of this year. While the initial release focused on sort of the high level architectures that can be commonly applied across a number of applications, I expect there's the next release will start to focus on a little bit more of some of the specific implementations, both in fully electric and hybrid electric. Next. Next work group is the safety considerations, which is an extremely broad topic, and you'll see that briefly on the next couple slides. This one, again, is focused on some of the things that are elements that are new and distinct from conventionally powered aircraft. I've already highlighted how some of the supply chain and subsystems have a relatively shorter history in aviation. So this committee is focused, for example, on fault tolerance analysis, failure mode assessment methods, and failure rate assessment methods, and how this all integrates up into an aircraft level safety analysis. Next. This gives you a little bit of the organization of the document and the roadmap timeline. This is, as I mentioned, a pretty broad topic. So we ended up pulling some of the system integration aspects out into a separate document that I'll talk about a little bit later. So this one is more focused at the component and equipment level analysis and how that might feed up into the system level and aircraft level work. Next. Next work group is one of the more recently formed ones, the endurance testing work group. Next. So endurance testing is a standard practice for conventionally powered aircraft. So this committee has been organized to develop endurance testing standards that will be relevant to electric and hybrid electric propulsion, since conventional is mostly focused on gas turbine and piston-based aircraft. Next. In order to provide the best utility for the industry and the authorities, this work group has decided to follow the same format that's been used for traditional endurance testing in terms of how the document's going to be organized. They're using a very similar design in terms of the test profiles, but adapted for electric propulsion motors and drives. Part of the activity that's going on in the work group is defining the boundaries of what will be tested, what kinds of measurement systems need to be included for an appropriate test, and then of course the waveforms that will be appropriate for electrified propulsion. For the first release, it's focused on fully electric, but that will sequentially move again to hybrid electric and highly distributed propulsion systems. Next. As I said, part of the safety analysis activity was pulled out into a new work group that was just established this fall. Next. So this committee is again just forming, but whereas all of the component and subsystem level safety analysis, fault tolerant, failure mode effect activities are being handled by the other work group. This is more looking at how those integrate into safety assessments at the aircraft level. Next. And part of the first scope activity of this group is, again, to look at what is already existing in regulatory language and in other committees to really assess either how to pull that together or address gaps. Next. All right, so I'll just close with some of the roadmap and way forward for the committee. Next. So this gives you an overview of the timeline for the active work groups, when they were established, when we've done our first balloting, and when we've had publication. Again, if you look in 2022, the first two documents have gone through their first publication phase. They'll have a synchronized second release towards the end of 2023. We expect those will likely have annual updates that are being fed by some of the activities in the other work groups. The next one, the third one, was again the safety analysis project. That one has been quite a long activity. Again, trying to narrow the scope in order to get a first set of useful standards out. We expect that to happen next year. The endurance testing one is rapidly moving to a first publication. We expect that in the first half of next year. And then we have the new aircraft level system safety and certification concerns group that is on a longer timeline and expect their first publication in 2024. Next. In terms of folks who might be listening to the webinar, we're always interested in having new members and participants in the committee. At our last meeting, we had 54 of the members attend our San Diego meeting. In terms of the work groups, the overall committee size is significantly larger, around the 150 plus member size. In the system safety activities, we definitely need some additional membership in some of the skill areas that we're starting to tackle now. In particular in the EWIS, the electrical wiring area. We're looking for some additional participants in that. As I said, the endurance work group, they're just about ready to finalize their first document that will go through balloting, and we have that new system that's kicking off. Also, that came out of our San Diego meeting, there's a number of other areas that we're potentially looking at starting a new document work group on. Next. So again, we worked through the pandemic virtually. San Diego was our first return to in-person meetings, and we typically rotate for our twice-a-year meetings between North America, Europe, and Asia. So the next meeting is going to be in Tokyo in the last week of March in 2023. Hope to see many people there participating with us so we can get some perspectives that maybe we don't get in person from that part of the world. And then the next meeting will be in Munich tentatively, and that will be in September of next year. Next. All right, thank you very much. Appreciate everyone's participation today, and look forward to questions. Thanks.
Thank you so much, Ed, for that great overview of all of the different activities going on with the E40 committees. If anyone has questions, feel free to pop them into the chat feature, and we will get to those later in the webinar today. So our next speaker is Mr. Olivier Savin, founder and CEO of Spirit Aerospace. Olivier is going to speak about the SAE AE7F Hydrogen and Fuel Cells Committee. So welcome, Olivier.
Thank you, Becky, for the introduction. Can you hear me okay?
Yes, loud and clear.
Okay. So I'm going to go into the details of the activities currently taking place within the standardization committee, AE7F, on hydrogen and fuel cells. I was given some teasing material from Pascal, but I will go more into the details of the actual activities. Next, please. So there's been a lot of talking about hydrogen and how relevant it is for transportation in general. I was thinking that maybe I could start off with a little introduction on why are we using hydrogen? Why are we contemplating hydrogen? So first of all, why use hydrogen as an energy carrier in the first place? Well, the beauty of hydrogen is that mixed with air, mixed with oxygen, it produces water. So it definitely is the ultimate environmentally friendly compound. Zero emissions locally and also globally if green hydrogen is being used in the process. Benefits for mobility. The other beauty of hydrogen is its high energy density, which converts directly into high range for transportation vehicles. Short refueling time, we're dealing with a fluid, not electrons. We're dealing with fluid, which is much easier to refill than electrons. And that translates into short refueling time, which obviously translates into convenience in the usage. Low operational cost, high availability, which yields low life cycle costs, and we'll discuss that later. The other piece of information that is worth mentioning is the fact that it's already being produced locally. There's more and more installations producing hydrogen for local applications. I'm thinking about utilitarian vehicles, trains, river shuttles, and so forth. So where and how to use this magic hydrogen and its converter, the fuel cell, in aviation? I distinguish basically two different avenues. The first one that I call the electric hydrogen. It's basically the use of hydrogen along with the fuel cell and the conversion of its energy into electrical power. And this can be used both onboard aircraft, but also as part of ground support equipment. Onboard aircraft, mostly for large aircraft onboard systems, such as replacement of auxiliary power units, producing power for galleys, emergency power, cabin loads. At some point, medical evacuation equipment was also contemplated. And also for smaller aircraft, it can be used in electric and hybrid propulsion systems, not only as the main source of power, direct drive, but also as a range extender equipment. What we've seen also is the emergence of usages on the ground within airport facilities for airport vehicles, ground car units, battery charging units, etc. The other avenue which is being contemplated is the use of hydrogen in its thermal form, in the sense that hydrogen is now combusted inside an engine, inside a turbine, to provide mechanical power. So on aircraft, we are, and it's part of what Pascal was describing earlier, we are actively contemplating the idea of using hydrogen as a direct feed into the engines. And it will basically emerge progressively from 0% to 100% mixed with jet fuel. The ZEROe at Airbus, the ZEROe program, for instance, investigates the path from 0 to 100% in 2035 on large aircraft. And also, as Pascal mentioned, hydrogen has a role to play also in producing SAF, sustainable aviation fuel, in the form of power to liquid scheme, which basically reflects the fact that hydrogen mixed with CO or CO2 can produce jet fuel in dedicated chemical reactions. Next, please. With this in mind, back in 2008, a handful of people created the joint SAE UK committee, AE7F on SAE side and Working Group 80 on UK side, to establish the grounds for the safe and airworthy use of hydrogen and fuel cell systems in aviation. So it's a dedicated task force that gathers basically half of the members from North America and half of the members from Europe. Our mission is to develop guidelines to support qualification and certification of hydrogen and fuel cell systems in any aircraft application. We've been able to gather representatives and experts from all the major stakeholders in the aerospace industry, not only airframers and system integrators, but also down to the component level, gas and hydrogen equipment suppliers, also research and test centers. The academia is also very well represented, and last but not least, certification agencies. Interestingly, from 2008, when we created the committee, there was only 5 or 6 members. We reached 80 right before the pandemics, and in the last 2 years, we've seen a very large increase in the interest of parties for hydrogen-related activities, and now we're securing more than 240 members. Not all of them are active members. I would say that maybe 50 to 60 members are actively working on developing standards, but yet there's a huge interest in this field. And the idea, of course, for us is not to reinvent the wheel, but to extend the experience that has already been gained in other fields of transportation, in automotive, truck, train sectors, and transfer all this knowledge into aviation. For instance, the understanding of the safe handling and operations. We are not going to reinvent the wheel, and we will definitely make use of existing standards that have been developed already in the automotive world, for instance. Likewise, we have gained some, the community itself has gained some thorough expertise in the development of systems, from the refueling part to operations on board, and obviously we will be using this knowledge as well. And we are making use also of a very profitable context where there's a rapidly growing hydrogen market going on, including related to the production of green hydrogen. So the idea is to produce relevant standards, safety guidelines, performance specifications, and specific focuses on dedicated technical areas, and I will go over that in a few minutes. Just a quick word about the organization. I've been acting as the chairman of this group since 2016. Co-chair is Mr. Masoud Sadeghi, a former FAA agent, more than 25 years in the authority. And our secretary is this gentleman from Ampaire, Carlos Morao. Next, please. So the first topic that we tackled, the first standard document that we produced back in 2013 was related to the aircraft fuel cell safety guidelines. It was issued in 2013 in collaboration between SAE and UK. Ed just mentioned the very key importance of giving the right definition to the terms being used in our work, and we followed the same approach. And one of the key items within this document is the definition of terms related to onboard fuel cell and hydrogen systems. In addition, the document provides technical guidance for the safe integration of one dedicated form of fuel cell, what we call the proton exchange membrane, PEM fuel cell systems. And the document includes sections on risk assessment, flammability considerations, design for safety. We decided to be agnostic regarding the type of storage, so both conventional liquid and gaseous hydrogen storage systems are contemplated. And with that, we have defined some installation considerations. What are the crashworthiness constraints, environmental constraints? What is the typical handling policy with hydrogen and the fueling processes to be put in place? This document was created in 2013 and it was reaffirmed in 2020. Next. Second second work that we conducted was related to the installation of fuel cell systems on large civil aircraft, only CS-25 aircraft, and it was in the form of performance specifications. Obviously, it was based on the previous work, but this time it provides detailed technical requirements for the design and installation of fuel cell systems on board large aircraft, CS-25 aircraft. We remained with the focus of PM fuel cell systems, which are the most mature at this stage. And we decided to stick to gaseous hydrogen, which is also the most mature of the technologies available today. In order to specify these performance specifications, we singled out our work to 3 given applications: medical evacuation operation, so power supply for medical equipment within business jets. We identified another key example, which would be the standalone galley power, completely isolated from the main electrical aircraft system. And the third example that we took was the emergency power system in case of loss of electrical power from aircraft engines. In other words, the replacement of a ram air turbine. It happens that this document will be reaffirmed. Hopefully, it will be reaffirmed next week as we are having our quarterly plenary next week. Next slide, please. At some point in the middle of the 2010s, we realized that decision makers were not ready to embrace hydrogen as a viable and credible option for airborne applications. So as a group, we decided to put together a document that would help them understand what are the benefits of using hydrogen on board aircraft. So we put together this comprehensive document to describe the applications of hydrogen and also to explain the benefits that it can yield in aircraft. So it basically covers why and how to use hydrogen and fuel cells in aviation by introducing the properties of the molecule itself, how to properly produce, store, and distribute it, what are the current hydrogen usages, both in the mobile world and in the stationary world, going to the details of what the hazards and mitigations are. And for that, we made use of the existing standards that had been developed in other fields of transportation, such as automotive, within SAE, for instance. And with that, we introduced the benefits of using hydrogen for airborne applications. Next, please. At about the same time, the FAA issued a very interesting initiative in the form of an ARC, Aviation Rulemaking Committee, in 2019, dedicated to the study of energy supply device. So experts were invited throughout the world to support this effort from FAA, which started in 2015. And around the table was gathered experts from the industry, experts from standardization committees such as ours, and also experts from governmental bodies, and namely EASA and FAA. So the idea of this effort was to put together recommendations with respect to the airworthiness and operational rules to be put in place in the forms of standards and guidance, to propose new requirements in a performance-based and prescriptive form for the regulatory bodies, and also identify the needs for change in existing requirements and associated guidance. The main focus was on fuel cell systems, but we tried to enlarge it to other type of energy supply devices. The report was finalized and officially published by the FAA in April 2019. I think it's still available online, of course. Next, please. So this is the past. Now I'm entering into what is currently being done within the working group. So we have started in 2019 an activity dedicated to the creation of a standard related to liquid hydrogen. So its title is Liquid Hydrogen Storage and Distribution on Board Aircraft. The work is still in progress. We are targeting June 2023 for the balloting phase. This document describes the general properties of liquid hydrogen and how a system needs to be designed so that it can accommodate for liquid hydrogen on board an aircraft. It specifies critical requirements for the safe use of LH2, liquid hydrogen, both on board aircraft, but also on the ground. And we are trying to contemplate all the different steps going from storage on the ground, distribution to dedicated refueling equipment into the aircraft, and contemplating the installation of such systems on board, their maintenance, their qualification, and their certification requirements. Next, please. In parallel to this effort, and because of request from a large population within the working group, we decided to put together another standard related to gaseous hydrogen storage and distribution in small aircraft. The work is still in progress. We started in September 2021, and we are expecting a balloting phase in September 2023. So this work is dedicated to the definition of guidelines for the safe integration, operation, and maintenance, and for the certification of gaseous hydrogen storage systems, high pressure systems in light aviation. We have decided to focus our work on light aviation, which probably is the entry point for hydrogen and fuel cell systems in aviation. So we are defining guidelines for the safe refueling and the safe operation of gaseous hydrogen on aircraft, but we are not addressing the question related to infrastructure, to distribution on airfields, nor how the refueling means are specified. Next, please. At the last plenary back in June, the group decided to go for another activity in parallel to the other ones. And it's again due to the fact that there are more and more projects emerging and which are based on hydrogen fuel cells for light aviation. So we decided to start this activity related to the use of hydrogen fuel cells for primary power and propulsion. The work is about to be initiated. I mentioned the plenary next week, so it will be the occasion for us to trigger this effort. Due to strong demand from members, we are not only going to contemplate the actual use of fuel cells for propulsion, but also for primary power for larger ones, which basically goes back to a follow-up of the previous document that I mentioned earlier. So the idea of this document would be to provide technical guidelines for the safe integration, operation, and maintenance, and for the certification of fuel cell systems used as primary sources of power on aircraft. Next, please. Just to wrap up, so we are an international standardization committee with an equal participation from North American parties and from European parties. We are aiming at establishing the grounds for the safe and airworthy use of hydrogen and fuel cell systems on airborne applications. Representatives from major stakeholders in the aerospace industry are around the table, and the members include hydrogen and fuel cell experts from all over the world, gas experts, certification experts. As I said earlier, the group has been increasingly active on this highly relevant topic that is hydrogen. And we are aiming at gathering the largest consortium of players because the larger, the better, and the larger, the more indisputable the consensus is among the stakeholders. So that's why I'm reaching out to the outside world the same way Ed just did before. We are welcoming new members, and the more, the better to contribute to the emergence of a sustainable future for aviation. Thank you very much for your attention, and I'm looking forward to questions.
Thank you very much, Olivier, for that great overview of all of the activities around the use of hydrogen and fuel cells. If anyone has questions for Olivier, please pop them into the chat feature and we will answer those later in the webinar. So our next speaker is Thomas Taylor. Thomas is the Technical Fellow at the Boeing Company and the AE10 Chairman. He will speak to us about the High Voltage Committee. So welcome, Thomas.
Thank you, and good morning, good afternoon to folks. As I mentioned, my name is Thomas Taylor. I'm a Technical Fellow for the Boeing Company, also AE10 Chair for the High Voltage Committee. So let's go to the next slide. So I'm going to play a little bit onto what Pascal provided in his overview and give you a little bit more details. This is a relatively new committee, as he indicated. We were just formed a little over a year ago. It really was formed to identify or address gaps in standardization for high voltage. So our scope for AE10 is really on the development of high voltage standards to support electrified propulsion and non-propulsive systems. And we're organized in, as Pascal had indicated earlier, into these 6 unique task groups. And as I mentioned, we're specifically focused on high voltage. Our goal is not to repeat the standards work that has been accomplished in other groups, but really focus on the uncharted territory for high voltage standards. And I'll be able to share a little bit more here momentarily regarding where that where is the definition of high voltage, at least as we define it within AE10. But I'll go through just quickly how we're organized. As Pascal alluded to, we are a new group, but we have roughly 209 members within the committee from all over the world that are supporting. And we're really working to collaborate and support the other groups. As Ed had mentioned earlier, E40 with electrified propulsion, we're very active in supporting that committee, and we're trying to become more and more engaged and support their efforts. But with regard to AE10, as described earlier, we do have task groups from the systems, energy storage, EWIS, which is electrical wire interconnection systems, equipment devices, user safety, and infrastructure. So for systems, these are all unique task groups they're covering a very, very large gamut of standardization for high voltage. So like I said, the intent is just to focus on high voltage. So for instance, the systems group really focusing on power source, network, power quality, environmental EMC, distribution of high voltage, actuation of high voltage. So that's the systems community. Next, the energy storage, as mentioned, looking at integration of batteries and fuel cells with respect to high voltage switching and so forth between multiple sources, if that is a part of an architecture. Electrical wiring connection systems. This is a very large task group. We have a lot of folks from AE8A and 8D that are participating that we're relying on for our standards development, but they're really focused on the uniquenesses and the issues associated with high voltage and electrical wiring connection systems, which is all aspects of the cabling, connections, support hardware, installation, so forth. And as you'll hear momentarily with the E11's overview, the specific concerns are with high voltage and partial discharge. And with that comes increased aging due to the stresses that are seen by these fields that are induced on the cabling in all the installation systems. So throughout all these different task groups, we're really looking or focusing on the effects of partial discharge. The next group, task group, equipment devices, looking at the machine itself, inverters, switching devices, and also passive components of capacitors, inductors, motor controllers, things of that nature. The next group, the user safety group. So understanding that high voltage introduces a lot of issues with respect to safety. And this is not just, this is the safety of the flight crew, the passengers on board the vehicle, also the ground maintenance crew and how they're going to maintain and operate in the aircraft, ensuring that we have safe procedures and standards in place to address the aspects of high voltage. Lastly, the infrastructure task group. That group is really focused on all the things that you need to do to manage and maintain and operate a high voltage system, high voltage aircraft, which would include charging, ground service, and also maintenance of that vehicle. So this is the task groups that we currently have that are active. Those are in process of developing standards. We're still, like I said, relatively new, so different from the other groups. We're still trying to get our traction, but we're moving forward and gaining more momentum. Let's go to the next slide. Okay, as we mentioned, or Pascal mentioned earlier, the High Voltage Coordinating Committee really is the overarching committee that provides direction for A10, including our high voltage roadmap. So in that, as I mentioned, it's really important to define high voltage. And so for the definition, we are pointing back to a document that was developed within AE7, which is AR 7502. This is a document that defines the voltage levels for electrified airplanes. So as you see there, currently the voltage levels that are defined are voltage 1 through 6. The voltage levels 1 to 2 are more traditional aircraft architecture, power system, where you're operating at known voltages. And for those, we have committees that address a lot of the have standards that address those voltages and the uniquenesses of those voltages. So we're not trying to repeat that work. As we transition to voltage level 3, this is where we start getting into an environment that is unique and that we do not have experience in industry and operating aerospace vehicles. Of course, there is a lot of experience in terrestrial high voltage, but in terms of aerospace and uniquenesses of the operation of the system at altitude and those phenomena that occur at altitude, that's where we're trying to fill the gap. So for our committee, we're really looking at the level 4. Look at the level 3, level 4 voltages and above. And the reason we're looking at level 4 now is that we understand the needs of the industry. And that's where, if we look to the right in the roadmap, which is the roadmap that is developed by the HVCC to really guide the A10. But we understand that the industry is really looking at development of these light aircraft and urban air transport aircraft, or eVTOLs. So those architectures or those vehicles and the architectures that support those vehicles are typically living in voltages between 400 to 1,000 volts. That's roughly where we're seeing most of the industry. So that's where our efforts are really focused, and that's where we've been trying to align our respective task groups to really focus their efforts. The roadmap then, as we understand that we're going to be ultimately looking toward electrification of larger aircraft. So you can see as we transition there from the urban air transport vehicles, the smaller vehicles, to the small commercial airplanes, it's going to require quite a bit more power. And as you do that, as Pascal indicated, as we move into the small commercial up to the mid and large transport vehicles, the power is increased dramatically. And as such, to ensure that we have the weight at a reasonable level to ensure performance of those vehicles, we have to have a much higher voltage. And those voltages introduce even more questions and more unknowns as we transition to upward above 1,000 volts up to 5,000 volts. But presently we're really living at about 600 to 1,000 volts is where we're focusing our activities for the AE10. Please, let's go to the next slide, please. And as I mentioned, the group is, or the committee is fairly new, and so we're first of all, our first task was looking at, first of all, what is high voltage, and then what existing documentation that was developed within other groups should be transitioned over to AE10 for the purpose of high voltage. So as I mentioned earlier, some of these standards, like I said, were developed previously. AR 7502, which is our overarching definition for electrified or high voltage aircraft, we're transitioning that over to AE10. In addition, we're looking at AR 7506, impact of high voltage on wiring, and effects of what like I mentioned, the aging aspects of high voltage with respect to partial discharge. Additionally, AS 7499, which was originally generated in AE7, we are also reviewing it for the high voltage aspect in regards to power quality, and that's been reviewed within AE10 as well as AE7. Additionally, we've moved over AS 8441, which is the minimum performance standards for permanent magnet propulsion motors and associated variable speed drives. ARP 7376, which is the design and test of high voltage power electronic systems, that was just initially initiated originally out of AR 6127, which is the document below, managing high voltage electric systems. These are, like I said, relatively new standards that were currently just initiated within AE10. The next one, ARP 7058, high voltage DC electromechanical solid state and hybrid switching devices in aerospace applications. That also was recently initiated and went through a first vote. We're still working through some feedback, and we're going to go out with another vote on AR 7058. The last one, arcing and isolation, which ARP, this is a new ARP that was just initiated this week within the committee, was really addressing uniquenesses of creepage. Of course, at high voltages, the concern not only just partial discharge, but electrical arcing and understanding the requirements for spacings, both with that like a terminal or within a connector. And this standard is aimed at looking at the testing for understanding the spacing or distances between different contacts or terminal connections for a high voltage system. So those are the current WIPs that are or published documents that are contained within AE10. As I mentioned, as we progress, we're getting more and more information or more feedback from the committee members on new AIRs. In addition, AE10 is also collaborating with E40, as it was mentioned before by Ed, ARP 8677, which is a safety consideration for electrified propulsion. We've been supporting that through our ambassadorship by identifying high voltage failure modes for electrical components. So currently we've had our EWIS organization, our EWIS task group, has developed a number of unique failure modes with respect to the EWIS components for high voltage, and we're providing that input to E40. But in addition, we're tasking the remaining groups within AE10 to do this a similar exercise, to identify the unique failure modes for high voltage components and provide that. And ultimately, within AE10, we will turn this into an AR or ARP as well to identify those failure modes in a more detailed sense, and that'll be a published document and forthcoming. Okay, let's go to the next. I think they're about. So, as I mentioned, we are relatively new. What we have in the works in the near term is next week I will be in Paris. We're conducting our second in-person meeting. We've had a number of virtual meetings, but we have this is our second in-person meeting in Paris, France, where we'll have hopefully a good membership participation. Our participation thus far in the virtual committee meetings has been roughly between 50 to 60. We're looking for more members and really active participation within the task groups. We have as with all of these committees, you see a lot of people in the committee, but we really were looking for folks that are passionate about high voltage and bringing that expertise that you offer and bringing it into the task groups and initiating new standardization work to address high voltage. So with that, I will close in just saying thank you for your attendance, and please reach out if you have any interest in attending or becoming a committee member of AE10 High Voltage. Thank you.
Thank you so much, Thomas, for that great overview of the AE10 High Voltage Committee and all of its many activities. Again, if you are interested in getting involved, please reach out to Thomas. If you have any questions, pop them into the chat feature and we will get those addressed for you. So we are going to take a 10-minute break here. The slides will count down on your screen, so we'll rejoin everyone in 10 minutes. Hello, everyone, and welcome back. Our next speaker is Dr. Weijun Yin, Chair of the SAE A11 Committee and Senior Principal Engineer retired from GE Research. Dr. Yin will speak to us about the electrical insulation in aging in high energy systems for aerospace applications. So welcome, Dr. Yin.
Thank you, Rebecca, for your introduction, and good morning and good afternoon, everyone. As Rebecca indicated, I just recently retired from GE. I'm still working on this AE11 committee, and hopefully soon somebody will take over the role. So today I will take this opportunity to kind of introduce what has been going on as the AE11 committee work and what has been covered, and also like to see feedbacks from the audience and the participation as well. So next slide, please. As Pascal and Thomas and also I think Edward earlier pointed out, really there is a trend in the electrical and hybrid electrical application, and that involves high voltages. So the high energy system here we define is really the high voltage or high current. So for example, the high current could be the superconducting in the future, but mostly at this point is kind of high voltage system to make an energy dense system. So what is included in the system has a power management, engine generators and motor-driven fans that has been discussed early on. And also the aircraft actually covered from, the small aircraft that was fly at a relatively low altitude, and then medium and large airplane that fly at higher altitude. So the condition and the power level it's required for those aircraft that can determine different requirement for the insulation system reliability. So to achieve this high voltage capable and altitude capable components, one key element is electrical insulation materials and the system. Basically, when we talk about system, is really the insulation materials coordination within the components or within the whole power system. So prime reliability is the key. So that is we're trying to address within the AE11 is how the aging of the insulation materials going through and what's aging process in each component within the power system. So next slide, please. So when we talk about the insulation system in the components, in A11, we cover, the E-width and electrical machine and power converters, but we're not going to discuss any insulation materials used in energy storage, for example, batteries and fuel cells, and also not going to discuss any superconducting system that's a cryogenic material, so we're not covered. Currently, we basically cover the components that is discussed in, mainly this three elements. But like I said, we are not talking about the components per se, but more of focusing on materials used in the components and how it is degraded over time. So next slide, please. I think this slide is kind of redundant as what Tom already pointed out in the draft AS7502 that kind of defined what is a high voltage level. So we want to be consistent of what we discuss in terms of say high voltage level, what is discussed. So what is different is Tom pointed out they are focusing on voltage level 4 for us to understand the insulation aging once it is above the partial discharge level that could happen. So mainly is above 300 volts above. It is what the partial discharge could happen. Although you can design the insulation system or components that is partial discharge free, but when we talk about the aging, initially designed for partial discharge free, and over time it may have other degradation mechanism trigger the partial discharge. So we kind of discuss it in the level basically from the level 3 and above. But there, once the partial discharge occurs, then insulation aging mechanism will be relatively same. It's only depend on the time level might be different. So the aging mechanism really doesn't change. So that's why we think, starting from level 3 and above, the documents we develop should be all relevant. So next slide, please. So what we are working on the AE11 currently is we have basically proposed 3 documents. One is AS3734, which is really providing an overview of potential failure mechanisms relating to the electrical insulation materials or system for high voltage aerospace application. So this is like we know we don't have a product in service yet. So there is no such aircraft that is already in service, which has a high voltage. That's what we defined in the previous page. However, based on the knowledge we have known on the sea level base, that we know what could happen when the partial discharge happens. So we kind of can mainly propose the failure mechanism based on the understanding what we had at the sea level, and then point out what could be the main aging stresses and the aging process in those components. So provide a guidance, say what indicators you can use once the materials has been aged. So through this document, basically give a general overview. And this document has been went through several iterations, and we hope that can be published next year, middle of next year, and probably early next first quarter next year we can distribute it for comments. So second document is more of based on the first document, see what are the main stress factors and what are the indicators. Then second document is say how to look for those indicators, what kind of test guideline that what we can provide. So this document basically provide a test guideline to see how to look for insulation aging and how to, what's the aging process that can show under the ACDC and PWM. That is very unique. The power electronics actually used in the aircraft system is is silicon carbide and those very fast switching semiconductor. And that is kind of, and also there is a combination of DC and AC. I will kind of show later on slides. So this document will be kind of emphasized on that aspect as well. So once we establish the test procedure, and then you can really now start to see how to do the accelerated aging and predict the life. That is critical to the design of the whole high voltage system and how to qualify it. So the insulation reliability is the main component of it. So we would like to have, at the end that can provide some of the guidelines, say, hey, how to predict life once you have the insulation system designed. So that is the outcome of the AIP 7380. And this one is, we are in the discussion, but have not started. I think in the progress-wise, 73, 74 will be first document released next year, and then follow up by the AIP 73, 75. And the last one will be probably take quite some time because usually it needs to have some longer term data really to support the model. So that's kind of the roadmap we have laid out in the AE11. Next slide, please. So this just kind of give you a snapshot in terms of what are the aging stress factors we consider. And that is, in general, this is a term as a team is everybody use it, is, thermal, electrical, ambient, and mechanical. So what is unique about aerospace application is really the ambient environment is very different than what is used at the sea level. And that in conjunction with the thermal is because the flight profile usually is thermal cycle is much shorter and faster. So in relevant to the sea level industrial application. So that is we kind of, when we look at those stress factors, we kind of look at what is unique to the aerospace application and what is common to the industrial application. So we can leverage the standards already developed for high voltage insulation system for the industrial application, and then how to incorporate it, adding the elements that is unique to aerospace. So let's go to the next slide to kind of illustrate what it is. So this is, the example is, for example, IEC 6505 is excellent document on electrical insulation system qualification for the high voltage system that is for industrial application. That means it is normally just used for the sea level power equipment. However, we have seen a lot of common stress factors. For example, what is the contaminants, that the interaction between the electrical and the thermal, right? And what are the contaminants and the defects due to the manufacturing that you need to consider. So if you're looking at the bottom, when we talk the electrical insulation system value, you basically need to look at the intrinsic breakdown that is normally used for the current low voltage aerospace basically component, right? So you're always looking at short-term breakdown and the electrical insulation resistance. Then once that passes, then it's good. However, if it is above partial discharge, the high voltage, then that's not good enough. So we will basically now looking at the surface and partial discharge, or you can call corona. And then also unique to it because it's a DC and a high power dense system. Although the voltage sometimes can be relatively low, but the thin film, then you can still have a high field that can cause charge injection. So those space charge and charge injection that mechanism could actually happen in the aerospace application. And then lastly, the cavity formation due to thermomechanical expansion or thermodynamic, that over the time during the surface can happen, right? So that can trigger partial discharge. So there is an interaction, and those have some elements that we definitely can use, leverage. So that is the direction we're going, and that is we will provide on the 7374 as well. However, the model that is established, based on the industrial application, whether it is applicable to the aviation application, that is very questionable. And we are, through the study, I think that is on the basically 7380 document, we want to give an answer, or at least some guidelines, say when it is applicable and when it needs to be modified. So so this just give you an example what would be working on in the on those three documents and what the scope would look like. And next slides, please. So I give for this one kind of go a little bit to detail from kind of go to more detailed from the last slide. Is then when we're talking about the aging model, really is we kind of combine all these three elements, all those 5 elements basically. So we know all the stress factors. The stress factors will depend on the flight profile, where the component located in the aircraft. And then the insulation materials used in those components, that could be different. That some is organic, some is inorganic. Then the reaction to it different, and also the intrinsic properties of the materials. So say breakdown, conductivity, permittivity, that's different. Or the material itself, whether it's partial discharge, resistant, or it's not. So that is. Then when we talk about insulation coordination, it is really how you design it, put it together, and the geometry impact. Lastly is accelerated aging test to generate the life curve. So once you have all those 5 elements, that you can start to build the model. So in the 70s, basically 73, 74 is kind of what we want to cover: stress factor, insulation materials characteristics. And then on the 74, 75, then we'll cover a little bit on the geometry and how do you make the coupon samples and how do you test it. And then include some, what is the accelerated aging factor you need to consider. So then lastly is, when you have everything together, then you can build up a model. So this is kind of just can give an overview what we were thinking, and really like to get the feedback from the audience, see what we are missing and what we should add to it. The next slide, please. So this gives you one of the example is what could be different when you're thinking about, say, for example, the electrical stress in power electronics. In the power electronics, say, power converter, we are not just consider about AC, we need to also consider about the DC and DC plus ripple. So this, in all this component, even within the power converter, you have subcomponents in there. For example, filters, DC link capacitors, bus bars, semiconductor module itself, gate drive, right, and all that, and the DVDT filter. So each materials in this subcomponent responds differently and under different conditions. So we just need to kind of have the test protocols developed for each, actually the material specific and the subcomponent specific. This kind of, just to give an example, is, when we're looking at, for example, I just kind of see, PD torrent or PD intorrent, it's really depend on the materials you used is purely organic, or it is inorganic or inorganic composite, organic or inorganic combined composite. Then the degradation rate is very different. So projected life would be different. So when we discuss about in the documents, we kind of separated that, and it needs to be more material specific. This is just the overall, just kind of give you to show how complex this condition might be for the electrical system. Even to come a common aging model is almost impossible. So it will be material specific. So that kind of naturally to my next slide is, what are the challenges in establishing insulation life model. So we know there is a lot of different materials used in various electrical components, like I have mentioned, and the multiple stress factors that impact, because each component or even subcomponent really depend on where it is located, what it is subject to, the environment. So when we talk about stress and how we test it in this different stress, that will be, kind of a lead to different failure mechanism and different degradation rate. So lastly, I think most important for us is, like I have pointed out early on, is we really don't have a service data available, or even not service data, even sufficient published data. We have very few published data available for the high voltage aerospace application. So when we establish the model, with how to verify those models will be a relatively challenging. So so when we it is always good to have the capability or ability to predict how long the insulation materials can last. But in the meantime, the verification is somewhat lacking. So that's the challenge, and so that also requires a knowledge. And I know, like, probably within each individual companies within working on this application have done some internal test results. Unfortunately, those test results are not available to the public and share in the standard document or even the test guidelines. So so this is something we are really trying hard to work on, and any suggestions, also any knowledge that can share, that will be really helpful. So that is kind of toward the end of my presentation, and thank you for your time, and really again, like I said, like the previous presenter said, like, we welcome all the feedbacks and the suggestion and the inputs. Thank you.
Thank you, Dr. Yin, for that presentation on the activities for the AE11 committee. If anyone has questions for Dr. Yin, please pop them into the chat feature and we will address those in a few minutes. Our next speaker is Mr. James Babinski, Vice President of Engineering with the UmbraGroup. James is going to speak to us about electric aircraft, SAE A6B3 mechanical and electromechanical actuation panel activities. So welcome, James.
Yeah, thank you for having me and allowing me to talk about the A6B3 panel or committee on mechanical and electromechanical or EMA activities. You can go to the next slide. Just a quick overview about our actuation panel and the panel leadership. I'm the chair. Errol Zatloff, who's with Curtiss-Wright Flight Systems, is our vice chair. Dan Roberts is our secretary, works with Eaton. So we've got a good smattering of people in our committee. We've got about 24 actual panel members that range all the way from a lot of tier 1 and tier 2 aircraft suppliers, as well as many people that are directly involved in aircraft and the airframers, Boeing, Airbus, Gulfstream. I'm sure I'm going to miss everybody, but that's what our panel is made up of. Next slide, please. Just a little, I'm not going to go through every word on our charter, and it's a couple slides long here. I'll just hit some of the main points. Our charter is actually, we're under the A6B Actuation and Control Subcommittee of the A6. So our panel at B3 is specific around to promote the advancement of mechanical, electromechanical actuation and control, to create standards associated with the design, manufacture, operations, and support of aircraft vehicles. Next, please. And really, and it's to create and maintain aerospace information reports, recommended practices, and standards. And so we recommend actual, to the government and other professional organizations to help them with some of their standards and organizations, and as well as converting military standards and specs to industry standards today. As we know, a lot of the military standards are being dropped or unsupported, and where applicable, we'll pick those up and generate an SAE standard where applicable. Next slide, please. So our charter, or our panel, actually, we actually provide a forum for a technical interchange of engineering knowledge for EMA technologies. Next slide. So really the scope will include, assisting the industry in specification, design development, and verification to support EMAs by providing documents that cover terminology, system descriptions, spec guides, components, test methods, and as well as lessons learned. Next, please. The scope covers all primary, secondary, and utility actuation on current and future manned and unmanned aircraft. So that's the key here, unmanned as well, spacecraft and missiles. And so we'll address mechanical, electromechanical, mechatronic actuation components that includes, all of the system and subsystem components like jack screws, ball screws, geared systems, brakes, clutches, electric motors, and all mechanical, the transmission components and the electronic drives, as well as feedback sensors. So the next slide, and the next couple slides, I'll cover a number of the documents that are important within our committee that we've authored and we continue to support and review and update on a 5-year basis or so. If we want to start with, and I guess I'm going to start from the newest and work backwards, but AIR 6052 is a document for trimmable horizontal stabilizer actuation description. So this is an information report that provides descriptions of THSAs, HSTAs, horizontal stabilizers, and pitch trim type devices. So these are all the ones in the tail of the aircraft that are installed on variety of transport and commercial and business aircraft systems. The second one, AAR 6016, description of high lift control systems. Again, this is another information report that covers high lift systems, so flaps and slats that are all involved in the high lift system. So it's again a similar document to AIR 6052, only it's covering other flight control type systems. ARP 5384 is a specification guide for power drive units. So again, this is a recommended practice on how to specify the design, performance, and test requirements for the power drive units that would drive flight controls and other utility actuation systems for aircraft, and it could be used on more than just aircraft, missiles and those type systems. AIR 5713, again a information report that's targeted on the in-service reliability data of continuously active ball screw and geared flight control actuation systems. So it's a report that was written that would provide up-to-date reliability data of continuously active ball screw and geared type actuation systems. So it's a report out there to kind of give you a guide around how reliable linear actuators and geared type actuators, EMAs, how reliable they really are in comparison to other types that may be fluid power related hydraulic type systems. So because there is a lot of things that in the EMA world that were, do we want fluid power? Do we want an EMA system or electrically powered system? There's a lot of differences between the two systems, and this is a report to help show that we do have good, reliable type systems out there. Next slide, please. ARP 5754 is document on electromechanical actuators, a specification guide. And again, this is another recommended practice that provides the characteristics and requirements and the design data to be recommended for inclusion into a specification that might be written for an EMA. It would also include its controls and monitoring of that EMA. ARP 4058 is a recommended practice based on mechanical geared rotary actuators. So similar to the previous electromechanical specification guide, this is a guide for mechanical geared rotary type actuators. So again, it would provide guidance in the preparation of requirements for the general design and performance and testing of geared rotary type systems. AIR 6226 is a information report regarding trimmable horizontal stabilizer actuators, again, THSAs or HSTAs or pitch trims, structural load path integrity monitoring principles. And again, this is an information report that is dedicated regarding the structural load paths and primary load paths, in the loaded zone of an HSTA or a THSA. Since it's typically a single point of failure within an aircraft, there are a lot of primary and then secondary and tertiary type systems in place to ensure a very high reliability of this type of a system. So this document describes some of the methods that would detect rupture, disconnect of some of these loaded paths, and a reference for existing solutions of implementation of some of these secondary and dual load path type systems. ARP 6131 is a recommended practice on maintenance and inspection procedures for rotary and linear mechanical actuators. So this recommended practice provides guidelines for the maintenance, inspection, and support of those type of actuation on in-service and aging aircraft. Next slide, please. ARP 5724 is a recommended practice on testing of electromechanical actuators, which are guidelines for to create specifications around the required testing of these actuators. So it provides overviews of the different types of tests and issues related to the testing of EMAs. And basically test methodologies to meet the test objectives. ARP 5812 is a recommended practice for actuators linear mechanical. It's the general specification guide as well. This is a recommended practice around about creating the design and manufacturing performance and test requirements of the linear mechanical actuators. So it's typically, this is the linear mechanical portion of an overall system. It may be like a distributed flap system on an aircraft where you've got a power unit, hydraulic or electric power unit in the fuselage of the aircraft. And you have, the distributed individual linear actuators out on the wings for actuating flaps and slats. So this would cover the design of these linear mechanical systems that are out on the wings. Since there are a lot of different types of linear type systems, ball screws, Acme screws, roller screws, rack and pinions, all those type of mechanical type actuators that are out on various areas of the aircraft. ARP 5777 is a recommended practice dedicated to the maintenance and inspection procedures for Acme screw type assemblies. So similar to the maintenance and inspection procedures for linear mechanical actuators, rotary and linear. This one's dedicated specifically to Acme type screw assemblies. ARP 5311 is a recommended practice that's the definition of mechanical actuation subsystems. So this defines all the relevant issues that affect the generation of an interface control document for mechanical actuation subsystems. It's a definition of documentations, drawings, reports, and design parameters to assure a successful development of a mechanical actuation subsystem. Next one, please. So we've got a number of documents in progress within our panel. AIR 6074 is a document, information report based on material selection and design practices for gear and jack screw actuation type systems. So this is a document that would focus on describing materials, heat treats, coatings, and all the relevant information that would be used in a lot of the EMA components for all of the linear type components, ball screws, Acme screws. It would cover, gearing that would be used. It would cover some of the transmission components, housing materials, all of those type of materials used in the linear mechanical type actuators. So it stops at the linear in the mechanical portions of the systems, and it wouldn't cover things like motors and other drive systems. AIR 8442 is an information report titled Considerations for Prevention of Moisture Damage in Aircraft EMA Equipment. And there's always this is a report that's being put together because there's always the back and forth where we have sealed or vented type actuators. What is the what is good and what is there's always the debate. Should we have a vented housing or should we have a sealed housing? And so this document provides a lot of information on a lot of methods to prevent the moisture damage. I know there's a lot of damage in control boxes where you get moisture and it turns to ice and it starts wreaking havoc on boards and chips and those type of things. So this is a document aimed at what happens with moisture. So ARP 7370, general guidelines for specifying motor requirements for electrically powered actuation. So again, a recommended practice around specifying motor requirements. AIR 7379 is a recommended practice regarding, or I'm sorry, an information report regarding seals and wipers for EMA actuators. So this is a document that would describe a lot of the methods utilized in creating specialized seals and wipers for mechanical components such as ball screws and roller screws. And it would include also the other parts of the mechanical actuators such as housings and the seals are static seals in housings. This isn't geared towards rotary type seals or standard type seals that you would see on rotary bearings or angular contact bearings or those type of products, but specialized wipers and seals that are specific to again some of these EMA components. AIR 7061 is an information report regarding failure modes for high lift actuation load paths. So this is one that is an information report to give a little guidance to people working in designs of these type of systems that would this document would provide typical failure modes that are seen in high lift actuation. So it would be an aid for creating FMEAs where you would have a report that would give you a lot of information regarding typical failures that have been found and or identified in high lift type actuation systems. So those are the documents that we've got in progress. Next slide, please. Some of the projects that we're looking at and are under consideration, and actually we're looking for help from an input from industry and other subject matter experts. As the top one here, where we're talking about a type of a recommended practice where we look for special recommendations on EMA type designs specific for electric aircraft and electric vehicles, whether manned or unmanned. There's a lot of these new type vehicles out, and that's what this this meeting is all about today, is some of these electric vehicles, and we would be looking towards authoring some type of a document dedicated within our panel on electromechanical actuation that would be applicable to these new type of aircraft. The second item, we'd be looking at a type of an information report around high efficiency system type considerations. Obviously, battery power and power is a big consideration in electric vehicles, and this would be a document that would talk about study of various losses that you would take into consideration in the different type of electromechanical actuation systems in order to try and create a higher efficiency type system. The last one here is an ARP that recommended practice around high voltage systems. Certainly we see a lot of up to 270 volt now, but we would envision a lot of these higher voltage type systems. I think that was talked about in the AE10 high voltage presentation, just one or two presentations earlier. So this where we would offer some guidance for these higher voltage systems in electromechanical actuation as well. But again, just a comment, we really would like to see some help and input from the SMEs in these areas. So that pretty much covers what we're covering in our panel. Go to the next slide, please. And what we'd like to do here is put an invite out for membership within our panel. Certainly, again, at this point in time, we've got 24 members, and those are the people that we have that are dedicated to writing new standards and maintaining the old standards. So any help we can get to help diversify the membership and bring on some additional panel members that are specific to electric vehicles and those type of processes, we'd really like to have you become part of our electromechanical panel. So we hold A6 panel meetings twice a year at various locations that we author and review the standards, our panel specifically to EMAs. The overall A6 group, which is, for aerospace actuation control and fluid power systems, within the A6 and the whole control and fluid power systems, it's made up of 10 different panels, handling everything from EMAs and EHAs and fluid systems, hydraulic type systems that are all dedicated to actuation and control of aircraft. So, and within these panel meetings, there's symposium topics that cover a lot of numbers of presentations dedicated to whatever that symposium topic may be. I think the upcoming topic actually for our next meeting in the spring, which will be in Arizona, would be a symposium talking about electric vehicles. And so along with the panel meeting, we usually find a venue close by to where the panel meeting is held, to where we can go and visit an airframer or a critical tier 1 supplier. We at the last meeting, we visited the Jet Propulsion Lab in Pasadena, so it's pretty interesting. So we are really looking to expand our panel knowledge from EV airframers and suppliers. So that's pretty much a concluding word from us. You can go to the last slide, which is has all my contact information, and anyone that would like to contact myself regarding the panel, A6 B3 activities, any of our standards, any of our recommended practices, certainly feel free to contact me. And also, if you'd like to join our panel, let us know. So thank you.
Thank you, James, for that great overview. It looks like the A6B3 committee has a lot of work going on. So like Jim said, we do invite anyone who's interested to reach out, and we will get you connected there. Our next speaker is Tim Davidson from SAE International's corporate sales team to talk to us about the SAE Mobilis and the SAE OnQ digital standard system. Welcome, Tim.
Hey, good morning. You can turn to the next one there. Next slide. All right. Hey, we had some great topics here covered, and just a personal thank you for everyone who sits on SAE committee. We couldn't do it without you. So where do I fit into this piece of the puzzle? We've talked about developing standards. Well, I'm more on the side of selling standards and SAE content. And we do that a couple different ways. One way, you can go out to just sae.org and buy our standards individually, one at a time. Those are single user license. So what I typically do is I work with companies like yourselves or on the call here today, more of the corporate solutions or maybe some smaller pack products, mostly because some of these standards are just being developed. You may not need all of them. So that's where a nice little subset may come into play. So on the screen here, SAE Mobilis is an open platform. That means you can actually go out there and search for free all you want. But if you are looking to download or have some type of subscription, that's where you then reach out to us and purchase either the full collection or smaller subsets. With SAE Mobilis, you have access to SAE standards, technical papers, ebooks, magazine articles, edge reports, and journals. So what I'll focus on here real quick for you today is probably the standard side, because when we started out with Jonathan here, he talked about the importance of the AMS standards and the aerospace standards, and also he said something about composite when it relates to these material, some of the materials being built. So AMS standards, we have over about 3,300 AMS standards. On the aerospace side, we have about 5,900 current aerospace standards. And then when it relates to the composite material, we have the CMH 17 books. Those are a collection of 6 books related to the composite side. We sell all of these individually, or we also sell them, like I said, as a collection. So I'd be more than happy to talk to you on those topics. These are yearly subscriptions with Mobilis, and it also includes daily updates. So you're always working with the most current information, which helps you when it relates to the AS 9100 and being certified and showing that you have something in place with your auditors. Well, also with the just real quick topic on the edge reports. Edge reports are kind of some new topics and that we have unsettled topics. We have 14 that relate to electrification and 17 that relate to aerospace advancements. I was looking at some of those titles and they're actually hitting on everything you guys were talking about today. And then to switch over to that next page, I don't know if it's on cue, Becky. You can keep on going. On cue, I'm just trying to speed this up for you, Beck. We have a lot more to cover still. So quickly on cue, basically what SAE has done, we are actually digitizing our standards. What this will allow you to do on your end is to integrate this information into like your internal databases. We do it two ways. One is with an API, which your database communicates with our database on this end, and it just has a seamless flow going back and forth. We also offer our own database here. It's called OnQ, and that allows you to go through and search for certain topics or maybe the AMS standard itself. And what that's going to provide you is we've actually split out the chemical composition, the properties, and the requirements. Typically something you would go through each PDF document within a standard and try to look for that information. We're doing that work for you, saves you time. And also you're able to export that information into your databases. So if you have any questions or if you would like to have a discussion about how you can get access to SAE standards, I'd be more than happy to help you find that solution. So Beck, wanted to get you back on schedule. Hopefully I didn't go too fast. Point of contact here if anyone needs access to our information.
Thank you so much, Tim. And again, there's Tim's information. If you have questions or interest in the standards, please reach out to him on the OnQ and the Mobilis platforms. So I'm going to talk a little bit about how to get involved in SAE's Aerospace Standards program. This is a nice little eye chart of all of SAE's Aerospace Standards technical committees. It's actually readable if you go on our website and pull it up. You can see all of the different committees at the highest level. A lot of these committees have subcommittees and task groups and work groups and writing teams under them, but this is a very high-level overview of all of those committees, and you heard from a number of them today. But if you're interested in getting involved in SAE standards committees, there are a number of different benefits to participating. One is, the ability to influence the global aerospace market by contributing to the development of standards. The networking with customers, partners, peers, suppliers, and regulators on these committees, gaining an overview of the industry itself, learning about state-of-the-art technology, and really staying informed of the technical standardization landscape as it progresses. So a lot of different benefits and reasons to get involved in standards development. And this is an overview of our standards process. I think you saw this earlier in Jonathan's presentation. It's a very straightforward process where we identify the need for a standard, form a committee to develop and draft that standard, go into the balloting process, and eventually to publication and out to the marketplace. So it's a very straightforward process, and when it comes to a revision, we start that process all over again. But if you are interested in getting involved in any aerospace standards committees, or even more specifically, some of those that were presented today, on aircraft electrification and or alternative fuels committees, you can contact Carrie Rohall at SAE. Carrie manages all of the committees, and her contact email address is on the screen there. So reach out to her or any of us on the call. Really, we can get you connected and linked into those different committees and wherever your interests lie. And we wanted to share also some additional resources on aircraft electrification and alternative fuels with you. SAE does a series of podcasts on a regular basis, and we have a couple. This one here is related to zero emission island hopping with sea gliders from Billy Thalmeyer, from co-founder and CEO of Regent. And Billy shares his groundbreaking wing and ground effect technology in episode 129 of the SAE Tomorrow Today podcast. These are all free podcasts available on the SAE website. So if you're interested in that one, there is a link there. You can just hop online and give a listen to Billy. We also have one on SAE, or Save Time and Reduce Stress by Going Vertical, from Tom Prevost, Air Taxi Product Lead at Joby Aviation. And you can learn about Joby's aerial ride-sharing service built around an electric aircraft designed to fly over congested highways and cities. So give a listen to that. We have one on fueling flight with hydrogen technology from Dr. Anita Sengupta, CEO and founder of Hydroplane. If you want to learn more about decarbonizing aviation for regional aircraft travel, give a listen to Dr. Sengupta. We also have SAE Edge reports, and these are really unsettled topics. There's one on general aviation and the transition to electrification. Unsettled domains concerning electric propulsion technology for commercial aircraft, unsettled issues regarding the certification of electric aircraft. So you can go online and check out those exciting new EDGE reports on cutting edge technologies. We have a couple of books that I wanted to highlight for you. The Electrification of Civil Aircraft and the Evolution of Energy Storage is one of our books. The Electric Aircraft Series, Fundamentals of Electric Aircraft by our very own Pascal Tallon, and Advances in Electric Propulsion. So you can check out those books on the SAE website also. And now we'll move on to some Q&A before we wrap things up here. So if you have any questions, I know there are one or two in the chat feature here. We'll go to those first. There was one, let's see here. For the E40 committee, it says, has E40 put forth any architecture guidance or definitions regarding system level or supervisory control functions that coordinate the control and operation of the various underlying subsystems, e.g. gas engine, electric machines, energy storage? Is system level propulsion control viewed as an aircraft level function?
Yeah, that's a great question. And I will say in issue 1, the description is pretty high level. And I know from the work group, there was some discussion about expanding that in the subsequent issue. But the intention is generally that the power distribution controller functional block that's described in AIR 8678 serves that supervisory control level in terms of conditioning power to the various propulsors. Like I said, I expect in the next issue there'll be further description about what we view outside the scope and part of the aircraft systems and what functions might belong in that power distribution controller. Thanks.
Great, thank you, Ed. There's another question here. This one was for AE10, but it looks like it may have been answered. It says, how high is the high voltage being considered, both AC and DC? But it looks like it was answered on slide number 83. So I think we're okay there. Let's see, the next question, looks like that one was typed in. So that's all we have in the chat feature. Does anyone else want to type in any questions in the chat? We can give you a minute here if you want to do so. It doesn't look like anyone's typing, so if you do have questions, feel free to follow up and email any of us on the call and we will get those answers for you. But as a wrap up, we will provide today's presentations along with a link to the video recording to everyone who was registered for today's webinar, so you can watch for that. And we will also issue a survey to you to get your feedback first on today's webinar and potentially what types of webinars you might like to see in the future from us. So if you could take a minute to just answer those couple of survey questions, we keep it short. And then if you would like to connect with the Ohio Aerospace Institute or SAE International, there's our website and our LinkedIn address. Feel free to contact us that way or follow us on LinkedIn. And otherwise, the OAI and SAE thank everyone for participating in today's aircraft electrification and alternative fuels webinar. Have a good day, everyone.